Hello, we will now do the 7-2 worksheet together. So I encourage you to try to do this worksheet, try to figure it out, to pause the video at various times to try to work a problem and then see if it matches the answer that I get. But so here we go. So this says context 1, 73% of high school students in a large school district plan on attending college. An SRS of 400 students is taken, and the proportion that plan on going is noted. So this, and of course, 7-2 deals with proportions. And so this is certainly a proportion. We have 73%. We have categorical data. Either they're planning on going to college or not. So that's categorical. So it says, draw a sketch of the sampling distribution of the sample portion and describe it. Remember to comment on its center, unusual value, shape, and spread, which is cussing. Anytime you have to describe a distribution, you should cuss. You should describe these 4 things, and that's what we're going to do. So the sampling distribution is going to be centered around P. There's our P, our proportion, which is 0.73. The sampling distribution is every value P hat could take. P hat is the sample portion that's going to estimate that. In other words, the proportion of the 400 that say they're planning on going to college. So we take a sample of size 400, and maybe our P hat is like 0.75 right up there, or maybe it's 0.71, or maybe it's 0.77, and so forth. The sampling distribution is every value that P hat could possibly take. And of course, this is explained more fully in the 7-2 instructional video notes. And so it will be approximately normal. All right, so these P hats, all the possible values of P hats we will say they're approximately normal, and the reason that they are approximately normal is N times P, so that would be 400 times 0.73, and N times 1 minus P, 400 times 0.27, and so this, in fact, is equal to 292, and this is equal to 108. They are both greater than or equal to 10. So that is in essence the central limit theorem. That's one part of the central limit theorem, is that all the possible values of P has to be approximately normal. It's N times P and N times 1 minus P are greater than or equal to 10. All right, so that takes care of, saying it is approximately normal takes care of the shape and also the unusual values. It takes care of the nature of the unusual values. So let's talk about its center. Well, its center is going to be described by the mean, which is 0.73. The mean of the P hats is equal to P, and that's equal to 0.73. And then lastly, the spread. How would you describe the spread? Well, you could talk about the standard deviation of the P hats. And the formula for that, which is on your formula sheet, is the square root of P times 1 minus P over N. And so that's going to be 0.73 times 0.27 divided by our sample size, which is 400. And so that, as it turns out, is equal to 0.022198. So we would write a paragraph, which I really don't have room for here, but you would just say the sampling distribution is approximately normal with a mean of 0.73 and a standard deviation of 0.022198. And there you go. That's how you do it. So what values of the sample portion will cause you to doubt the 73% figure? Well, in general, our rule of thumb there is if you go beyond 2 standard deviations, 2 or 3, something like that. But we'll say if you go beyond 2 standard deviations. So if in general, so if you go out 1 standard deviation, it's going to, so if you add, 0.73 plus 0.022, let's say, so that'd be 0.752. Anything above that, that would be one standard deviation here would be 0.78. If we go out 2 standard deviations, which I'm going to calculate in a minute, when you get a value, a P hat value, if your sample value is way out on the tail, either the right tail or the left tail, it's causing us to doubt that this might be true because it's so unusual. So values that are way out on the tail cause us to doubt whatever is claimed in the problem. And in general, how far out on the tail you got to be? In general, about 2 standard deviations. So we will say that. So if I go anything greater than, if I say the mean, 0.73 plus 2 times the standard deviation, 0.022198. And so that would take me to 0.7744. That's 2 standard deviations above the mean. Anything beyond that's unusual, and it would cause us to doubt the claimed proportion. And so, or anything 2 standard deviations below the mean, which would be 0.73 minus 2 times that, 0.022198. And that would be anything less than 0.6856. So anything greater than that or less than that would be really unusual. It would be really way out on this tail and cause us to doubt the 73% figure. All right, so let's look at this problem. So this says in the sample of 400 students, 300 of them, 75%, say that they plan they're going to college. If the 73% figure is correct, what is the probability of getting a sample portion this large or larger just by sampling variability? And does this give us reason to doubt the 73% figure? So what is happening here is here's our sampling distribution once again, like this. It's centered at 0.73. Like that. And so 0.752 is about right there. That's 1 standard deviation above the mean, halfway down that hill. Well, 75% is going to be like right here. Right there. So there's 0.75. And so we want to know the probability of getting that sample proportion that large or larger. And that is in essence asking for the area of the normal curve that is above 0.75 or larger. Okay, so how do we figure that? And that's normal CDF. From 0.75 to infinity, our mean is 0.73, and our standard deviation, just like we found up there, 0.73 times 0.27 over 400. And of course, label this as lower bound, upper bound, the mean of my p-hats, the sigma of my p-hats. Like that. And that would be properly labeling it. And so let's use our calculator to find that, just like we've been doing a lot since chapter 2. So of course we go to the distribution menu, which is above the vars button. So we go second vars, which is distribution, and go to normal CDF. So we go 0.75 to infinity, which is just a big number, and then 0.73, and then we put the square root of 0.73 times 0.27 divided by 400. So like that. And so we would get 0.183799, like that. And so that would be our answer. Okay. Does this give us reason to doubt the 73% figure? And like I just said, anything way out on the tail out here will cause us to doubt it. Okay. But this is certainly not way out on the tail. So we wouldn't have reason to doubt. In other words, to doubt the 73% figure. It's very plausible that the difference between 0.73 and 0.75 is due to sampling variability, just random chance. Okay. And what this number is the probability that, assuming the 73% figure is correct, that we're going to get a value this big or bigger. And that's a pretty decent percent chance. If this number was less than 0.05, that there was less than a 5% chance that we would get a value this big, we would say we'd have reason to doubt the 73% figure. So the way, does this give us reason to doubt the 73% figure? And this is what we're going to say. No, it does not. No, because 0.183799 is greater than 0.05. And so it's reasonable to happen by sampling variability. As a matter of fact, I will write that here. That would be sort of stating it completely. So it is reasonable to occur by sampling variability. Sampling variability, or just random chance. It's not the neatest thing in the world, but so there you go. Okay, let's look at number 4. Okay, in another sample of 4,000 students, so the sample size they multiplied by 10. They were doing 400 students. Now they're doing 4,000 students. All right, so 3,000 of them, which is still 75%, say that they plan on going to college. If the 73% figure is still correct, what is the probability of getting a sample portion this large or larger just by sampling variability? And just give us reason to doubt the 73% figure. Well, we're going to do the same thing we did up here, except we're just going to change our sample size to 4,000. So that's just going to be normal CDF from 0.75 to infinity. This is 0.73, and this would be the square root of 0.73 times 0.27 over 4,000. So our standard deviation is a lot smaller now. It's lower bound, upper bound, the mean of my p-hats, the sigma of my p-hats. And so let's see what this is equal to. So as a matter of fact, I'll just call up that last command and just change this to 4,000. Just insert another 0. And so it gives me, look at that. So that's 0.00021918. So this is saying there's, it is very unlikely to occur. If the 73% figure is correct, the probability of getting 75% or bigger with a sample of size 4,000 is very unlikely, well less than like 1/5 of 1%. Okay. And so does this give us reason to doubt? Yes, it would. Yes, it would, because 0.00219 is less than 0.05. So it is unlikely to occur by sampling variability. In other words, by just random chance. So what's happening here is this, is that even though we have the only thing that changes the sample size. So in both of these distributions, so here's the first one with a sample of size 400. So with the sample, here's our sampling distribution centered at 0.73, and 0.75 is like about right here. So there's 0.75. And so it's reasonable. The probability of that occurring or larger is reasonable. What's happening with a sample of size 4,000, and every value on here is a p-hat. Every value, all these points in here are p-hats. That's what a sampling distribution is. But now with 4,000, what's occurring it's scrunching together the p-hats. So here's 0.73. And so our p-hats are really scrunched in there, because when you increase your sample size, your variability goes down. And so now our distribution is going to look something like this. It scrunches them all together to where now 0.75, the area outside 0.75 is really small. So in a sample of size 4,000, the probability that you get 0.75 or more, assuming 0.73 is true, is very small. And so if you do get a p-hat out here, it gives us reason to doubt the 0.73. But with a sample size 400, it wouldn't cause us to doubt it. And so the reason is that there's less variability in the sampling distribution. So there you go. And so that's what this is getting at here. Why are the conclusions drawn from number 3 and number 4? Why are they different, even though the sample proportions are the same? And that's just what I demonstrated there. And the answer is this. It says the larger sample size creates less variability in the sampling distribution. So a value a certain distance above the mean, here 0.03, so actually it's 0.02 above the mean, because that's how far it is from 0.73 to 0.75, or higher, is less likely to occur. Okay, so that is how you could word that. So there you go. All right, so let's go on to number 6. So number 6 says this. It says in Alabama, 78% of the state workers are satisfied with the state pension plan. In Mississippi, 72% of the state workers are satisfied with the state pension plan. An SRS of 400 workers from Alabama and an independent SRS of 500 workers from Mississippi are taken. Let p-hat sub A represent the proportion of workers in the Alabama sample that are satisfied with their pension plan, and let p-hat sub M represent the proportion of workers in the Mississippi sample that are satisfied with their pension plan. Describe the sampling distribution of the difference in the proportions. So we've got two samples here. We got two populations. The population number one is all the state workers in Alabama. Population number two is all the state workers in Mississippi. And so these are population values. These are P proportions. So I'll call this P sub A. The population portion for Alabama is 0.78. Okay. And so then P sub M, that's going to be the population portion from Mississippi. And so that would be 0.72. Okay. And then the sample size, he has 400 from Alabama. So the sample size from Alabama is 400. And the sample size from Mississippi, so the N from Mississippi is equal to 500. Okay, and so what the sampling distribution here is this. It's every value this difference could take. In other words, if you took one sample, now we're expecting the difference to be 0.06. I mean, because that's how their means are different. Okay, so we're expecting this to average 0.06. But in our sample, it's going to vary. The difference is going to be around 0.06. And if you took many different samples, you get many different differences. So I'll put D for difference. We'll say this is represented by difference. And this is the sampling distribution right there. Now, it will be, first of all, and so we're asked to describe the distribution. So we have to cuss. So the center of this distribution, the center of all these numbers is, so the mean of the difference, which is P hat sub A minus P hat sub M. You just subtract the population values. That's going to be 0.78 minus 0.72. So that's 0.06. Okay. Now let's talk about the spread. So what is described by the spread? So that is going to be the standard deviation of P hat sub A minus P hat sub M. And the formula for that is on your formula sheet. And so let me show you that. So on page 2 of your formula sheet, and so it is, so when you're dealing with proportions, and so there it is. So to get the mean, you subtract the two population values, and then there's the formula for the standard deviation right there. And so you can just plug it right in. It's a little complicated, but it's okay. And so this would be the square root of 0.78 times 1 minus that, which would be 0.22 over 400 plus, and then it'd be 0.72 times 0.28 over the sample size there, which is 500. And so that, in fact, is equal to approximately 0.028849, if you were to find that. And then, so we've got that. What about this shape? Okay. It will be approximately normal. And you just have to memorize this. If n times P and n times 1 minus P for both of our populations are bigger than 10. So what you would say is 0.78 times 400, and then 1 minus that, which would be 0.22 times 400. So that's just P, that's P, and that's 1 minus T times the n. And so then you would have 0.72 times 500. And then 1 minus that, which would be 0.28 times 500. And all these are going to clearly be bigger than 10. This would be 312, and that's 88. And then that is 360, and that's 140. And so they are all greater than or equal to 10. So by the central limit theorem, our sampling distribution will be approximately normal. And by saying it's approximately normal, that takes care of the unusual values, where that describes the nature of the unusual values of the outliers as well. So what you would say is, to describe the sampling distribution, you would say the sampling distribution is centered with a mean of the differences is 0.06. The spread is described by the standard deviation of 0.0288. And then the shape would be approximately normal, and that's it. That's how you would do that. And so now that we have that sampling distribution, it'll allow us to do a problem like this. What is the probability that the sample portion of Alabama workers that are satisfied with their state pension is at least 0.1, which is 10%, greater than the sample portion of the Mississippi workers. So it's just saying, in other words, what's the probability if you were to randomly select one of these differences? And these differences, once again, are Alabama minus Mississippi. So if Alabama is 10% greater or 0.1 greater, so 0.1 is going to be somewhere up here. So there's 0.1. So what's the probability it's going to be that or greater? So we've got to find that area. And so we will say normal CDF. And 0.1 to infinity. Our mean is 0.06. And our standard deviation is going to be 0.0288479. So that is our lower bound. That is our upper bound. That is the mean. And I'll just say mean of the differences, since I've defined that D as being what that is, and then sigma of the differences like that. And so let's see what we get. And so we'll go second VARS, which is distribution, then go normal CDF, and we are going 0.1 to infinity. And so this would be 0.06, and then this would be 0.0288479. If you can see that, but that's what it's saying. And so then we just hit enter a couple times, and it gives us our answer. And so that would be 0.08278. And that is that, which is above 0.05. So it's a reasonable thing to occur. It gives us no reason to doubt the claims of this problems. And that's it. That is it for the 7.2 worksheet. And thanks for watching the video. If you got any questions, please send them to me.